Hello dear students, welcome back to your physics class. Today's lesson we're going to talk about diffraction in section 2 chapter 7, diffraction and the bending of light. First of all, let's define the diffraction. What is diffraction? A change in the direction of the wave when the wave encounters an obstacle, an opening or an edge that spreads behind these obstacles. Another definition of diffraction: the spreading of waves behind obstacles as thin wires, for example, or small opening or sharp edge. For example, assume that this is obstacle, okay, and this is a screen. When the light pass in this direction, for example, this is the source of light and this is the portion of the light wave. Whenever the light hits this obstacle, okay, or this sharp edge, the light does not move in a straight line. Instead, it's going to be diffract, okay? So what is this? This is the diffraction of light, okay? This is diffraction of light wave. The bending or diffraction of the waves occurs in both types of wave, mechanical and electromagnetic waves. So it means that the diffraction will occur in all types of the waves, such as mechanical wave or electromagnetic wave. In mechanical wave, the bending of the sound wave or diffracting of the sound wave, which is longitudinal wave, and the water wave. An example of mechanical wave also, the water wave can diffract or can bend when it encounters a sharp edge or small opening or something like this. Electromagnetic wave also can be diffract, like such as a light waves, okay, or other types of the electromagnetic waves. Why, if you stand near the corner of a building, you can hear someone who's talking around the corner, but you cannot see the person? What is the reason? So, for example, when you are standing near a corner, okay, of a building, you can hear someone, even if you don't see this person, but you can hear him when he's talking, because the sound wave has more wavelength and has more diffraction, okay? So the reason or the answer, because the sound waves are able to bend around the corner more than, the bending of the sound wave is more than the bending of the light wave. Water waves bend around obstacles. Light waves can also bend around obstacles. The bending of the waves can occur in all types of wave, such as mechanical or electromagnetic wave. Why the bending of light is smaller than the bending of the sound wave? Which one has more bending, sound wave or electromagnetic or light wave? Absolutely, the sound wave has more diffraction or has more bending, because the bending of the wave is directly proportional to the wavelength. So which one has more wavelength? Absolutely, the sound wave has more, its wavelength is bigger than the wavelength of a light wave, okay? And wavelength is directly proportional to the diffraction, okay? More wavelength has more diffraction, okay? So that is why you can hear someone is talking even if you don't see him, but you can hear him, okay? The bending of light as it passes through each of the two slits can be understood by the Huygens principle or Huygens principle. What is the Huygens principle? This definition is very important. Be careful. Any point on a wavefront can be treated as a point source of the waves. Any point on a wavefront can be treated as a point source. For example, we have a source, a light source here, okay? And we have a barrier. Let's do some small opening or some small hole here. Let's gonna do some slit. How many slits do we have? 4. 1, 2, 3, 4, 5. Sorry. So when the light encounters this small opening, so the light does not travel in a straight line, okay? And instead, it's gonna be diffract like this. In this small open also, it's gonna be diffract. For this one also the same thing. Okay, so what is this? This is the Huygens principle. Any portion, any point on the portion of the wavefront can be treated as a point source. Now here we have one source, but in this 5 holes, each hole acts as a new source. Now how many sources do we have? We have 5 sources, okay? So according to the Huygens principle, any point on a wavefront can be treated as a point source of the wave. According to Huygens principle, each portion of the slit acts as a source. Hence, the light from one portion of the slit interferes with the light from another portion. Then if the path difference is equal to integer multiple of the wavelength, if path difference is equal to 0 wavelength, 1 wavelength, 2 wavelength, 3, okay, an integer number of multiplied by wavelength, so this interference becomes constructive interference, okay? The constructive interference and the bright fringe appears. But in the case, if the path difference is equal to an odd multiple by half wavelength, if path difference is equal to, like, for example, 1 over 2 wavelength, odd number multiplied by half wavelength, 3 over 2 wavelength, another odd number, 5 over 2 wavelength, and so on, okay? So this, if the path difference is equal to an odd multiple half wavelength, the type of the interference becomes constructive interference and the dotted fringe occurs. The resultant intensity of the diffraction light on the screen depends on the angle through which the light is diffracted. In general, diffraction occurs when the wave is passed through small openings around obstacle or sharp edge. When the slit is 1 millimeter or more, is placed between the distant light source and the screen, the light produces a bright rectangle with the clearly marked edge on the screen. So if the slit is gradually narrowed, based on this equation, if you remember, we studied in section 1, m lambda. Theta is equal to what? Sine inverse m lambda over d. Guys, this is the angle of diffraction. What is the relation between angle of diffraction and the distance between the slits? Is inversely proportional at constant order number and wavelength, okay? More distance, less angle of diffraction, and the bright pattern becomes narrowed, okay? But less distance, the pattern becomes wider and the angle of diffraction increases. As you can see in these two figures, we have two open, okay? This open, the distance of this open is greater, but it has less diffraction, okay? The diffraction is less. As we decrease the open, or when the open becomes narrowed, what's happened to the diffraction? The diffraction increases. When d decreases, what happened to the theta? Increases. So based on these three figures, if they bring in the exam, which figure the distance between the slits is very narrow, or the distance between the slits is narrowed? The third figure, okay? This one, the distance between the slit is very narrow, and this one, the distance between the slit is wide, okay? This is wide. What do you mean by wide? It means that d is more, but theta is less. And the bright fringe becomes narrowed because theta is decreases. As the slit width becomes narrow, it means d decreases. What happened to the theta? Increases, and the bright pattern becomes wider and more clear. The amount of diffraction depends on the wavelength, directly proportional. Wavelength with theta is directly proportional at constant m and d. As the wavelength increases, the amount of diffraction also increases. Theta is equal to sine inverse m lambda over d. If d is constant, order number also constant, what is the relation between angle of diffraction and wavelength? Is directly proportional. Directly proportional. Which color has more diffraction? Absolutely the red color. Why? Because red has more wavelength, okay? So which color has the smallest diffraction? Absolutely the violet. Why? Because the violet, its wavelength is less, okay? Less than the red light. Theta of red is bigger than theta of the other colors, like violet. Because lambda, the wavelength of red, bigger than wavelength of violet. The diffraction becomes more evident. The diffraction becomes more evident as the width of the slit is narrowed. It means theta increases. As the width of the slit is narrows, the width of the fringe will be wider, increases. Why? Because theta increases. Okay? So, guys, look. The width of the the width of the fringe is wider here. Why? Because the distance of the slit is narrowed. Okay. As the width of the slit is narrowed, the amplitude and the angular displacement increases. The amplitude also increases. Okay, as the width of the slit is narrowed. The further away from the center, the light intensity of the fringes decreases, because intensity inversely proportional to the square distance from the source. If the light traveled only in a straight line, you would not be able to observe the interference like this. Okay, if the light passed like this without diffraction, you cannot observe the interference of this light. But actually, the light do not travel in a straight line. Okay, instead you would be saw the interference pattern in double demonstration. Instead, you would see the two thin strips, okay, of the light, where each slit and the source were lined up perfectly. In a diffraction pattern, the central bright fringe is twice as wide of the secondary bright fringe. In diffraction pattern, the central bright, guys, look, this is the central bright, M0. The central bright is twice as wider the secondary bright fringe. In diffraction, the pattern, the central bright fringe is twice as the secondary bright fringe. The angular displacement directly proportional to the wavelength. More angle has more angle of diffraction. Sorry, more wavelength has more angle of diffraction. Assume that this is a small open. Okay, look. This is the small open, so we have 5 portions of the light. Assume that. So we magnify this figure. This is D, the distance of the slit, or the width of the slit. When the light passes through this open, what's happened to the light? The light is gonna be diffract. Okay, so when the light is diffracted, the path difference, if the path difference is equal to integer multiplied by wavelength, bright fringe occurs and the type of the interference becomes constructive. But if the path difference is equal to an odd multiple by wavelength, half wavelength, the destructive interference occurs and the direct fringe appears. To understand the single slit diffraction pattern, as you can see in this figure shown below, which shows that an incoming plane wave passing through the slit of the width, each point, or more accurately, each infinitely thin slit with the wide slit is source of the Higgins wavelet. The figure is simplified by showing only 5 amounts of the portion of the light. As with the double slit interference, the viewing sequence is assumed to be so far from the slit, and the ray emerging from the slits are nearly parallel. At the viewing sequence midpoint, all rays from the slit travel the same distance, and the bright fringe appears at the central Okay, so M0 is always bright. The wavelet from the 5 sources can also interfere destructively when they arrive. The sequence as shown in the figure B, when the extra distance traveled by the wave orienting 0.3, half of the wavelength longer than from 1. So in this case, the type of the interference becomes destructive and the direct fringe occurs. Question 11 in chapter review: why does light produce patterns similar to an interference pattern when it passes through a single slit? Because at a certain angle, the diffracted waves from different part of the slit destructively interfere with each other, forming what? Direct. Okay? If the slit destructively interfere with each other, forming what? Direct fringe, like this observed in the interference pattern in double slits. Both patterns are produced by diffraction if the constructive interference occurs and the bright fringe produced. But if the destructive interference occurs, the direct fringe produced. Which one has, so the similarity between the single slit and the double slit interference, both of them can be used to demonstrate the interference of light, direct fringe and the bright fringe. Which one has more angular displacement? Theta. Blue or yellow? Theta, blue or yellow? Which one has more? Absolutely the yellow. Why? Because according Roy GB, red, orange, yellow, green, blue, indigo, violet. Red has the longest wavelength and violet is the shortest wavelength, but yellow has more wavelength comparing with the blue. So because wavelength of yellow is bigger than the wavelength of blue, so that is why the yellow color has more angle of diffraction. The yellow color has more angular displacement, angle of diffraction. The light diffracted by an obstacle also produces a pattern. Look at this fit, guys, be with me. Look at this fit. We have a small open, okay? And we have a screen here, okay? And also we can control this small open. We can widen the open and narrow the open, okay? This is wider, and it becomes also becomes narrow, okay? When the open becomes large, it means that D increases. More area, more diameter, it means that more D, okay? More D, less theta. So in this case, we can use the red light. Look, you can see the interference of the light. When the light encounters the small open, okay, or small open, what's happened to the light? The light is going to be interfered, okay? So which type of interference? Destructive and constructive. The dark fringe represents for the destructive interference, and the bright fringe indicates the constructive interference, okay? In this case, as we decrease the area of the small open, if we decrease the area of the small open, it means that D decreases. When D decreases, what happens to the theta? Theta increases. When theta increases, the width of the pattern also increases and becomes wide, okay? As we decrease the small open, what happens to the pattern? Increases. The width of the pattern increases. Only by changing what? By changing the distance of the slit, okay? If we increase the small open, diffraction decreases and the width of the pattern also decreases. But if we decrease the small open, when the small open gets more narrowed, what happened to the theta? The theta increases and the pattern, the bright fringe, becomes more evident and more wide. But at constant D, if we decrease wavelength from red to violet, if we decrease the wavelength, what happened to the pattern? The pattern also decreases without changing the distance of the slit. Without changing the distance of the slit, can we change the width of the pattern? Yes, absolutely. By changing what? By changing the source of the light, by changing the color of the light. When the source of the light changes, wavelength also changes. Which one has more wider pattern? Absolutely the red color. Why? Because red color has more wavelength, okay? The violet has the smallest angle of diffraction and the smallest bright pattern because its wavelength is too less. Let's go back to our pamphlet. Look. Okay. Diffraction occurs around the edge of the all objects. Figure shown the small open, the bright fringe, and the dark fringe. Diffraction grating, another topic. What is a diffraction grating? And diffraction grating is a device, it is transparent material that can be used to demonstrate the interference of the light and the diffraction of the light, and also can be used to disperse the white light into the spectrum. Why does the light disperse into the streak of the colors when it falls on a compact disc? Why does the light disperse into what? The streak of the colors, the spectrum, when it falls on a compact disc? Because the disc, this compact disc, reeled with many lines, so each line acts as a diffraction grating, because when the white light is reflected from the disc surface, each wavelength of the light can be seen at a particular angle with respect to the disc surface, causing you to see a rainbow on the spectrum. What does the constructive interference on the compact CD disc depend on? It depends the orientation of the incoming light, the orientation of what? Of the incoming light when hits the compact disc, and the orientation of the disc, okay, and the light's wavelength. What is diffraction grating? A plate of glass or transparent medium. Diffraction grating, a plate of glass Okay, assume that this is a plate of glass or metal reeled with very close parallel lines. Reeled with what? Many close parallel lines. So what is this? This is diffraction grating. A piece of metal, transparent metal, that reeled with the many closed lines, parallel lines, producing a spectrum by diffraction and interference of light. Constructive interference by diffraction grating. Light of a single wavelength pass through each of the slits of a diffraction grating to constructively interfere at a particular angle and destructively interferes at a particular angle. So assume that this is the lines, okay, the reeled by, reeled, okay. When the light passed from each slit, what happened to the light? The light is going to be diffracted. So in this diffraction, because of the path difference, dark fringe and the bright fringe occurs on the screen. How is diffraction grating generated? A transmission grating consists of many equally spaced parallel lines. These gratings are made by reeling equally spaced lines on a piece of glass using what? Diamond cutting. By diamond cutting, we can reel this metal, driven by an elaborate machine called a drilling engine. What are the uses of diffraction gratings and the applications of the diffraction grating is very important. To measure the wavelength of monochromatic light. The wavelength of what? Of monochromatic light or a single light, single color light. Can be used in a spectrometer. Also, a spectrometer is a device we will study inshallah. And also can be used to disperse the light into it is component of the colors. When the white light passes through the diffraction grating, what happened to the light? The light can be like separated into many colors. Okay, so each color has its own angle of diffraction or angle of displacement. What does the angle of diffraction grating depend on? The angle of the diffraction grating depends on what? Theta is equal to sine inverse m lambda over d. It depends on the order number, wavelength, and the distance between the slits, or the distance between the lines. With m is directly proportional, wavelength also directed, but with the d is inversely proportional. What happens when the monochromatic light falls on diffraction grating? If the path difference between the two waves are equal 0 or some integral multiple wavelength, constructive interference occurs and the bright fringe will be appeared on the screen. For the first one, constructive interference occurs. Why? Because the path difference is equal to 0 or integer multiple wavelength. Because wave from the slit will be in phase and the bright lines will be observed. So what happened to the diffraction grating? If the path difference is an odd multiple by wavelength, the destructive interference occurs, and because the waves form all slits will be out of phase, and the dotted line will be observed. This equation can be used for the bright fringe and this one for the dotted fringe. Constant grating, what is the constant grating? The distance between the slits. The distance between what? The distance between slits. This is called the constant grating. Okay? This distance is the distance between the gratings. All distances should be the same. The distance between two slits equal to the inverse of the number of lines. More number of line, less distance. Less number of line, more distance. Here we have more distance, and also we can make another diffraction grating with the little lines. Okay, so we have two diffraction grating. One of them, the first diffraction grating, has many lines, and the second diffraction grating has a few lines. So the first diffraction grating has more number of lines, the second one less number of lines, but the second one has more distance between the lines. D is more here, but D is less here. Okay? As the number of line increases, what happened to the D? D decreases. As the number of line decreases, what happened to the D? The D increases. Okay? So that is why D is equal to what? D is equal to 1 over number of line, because inversely proportional. Number of lines. And number of lines is equal to what? The same thing. Number of lines is equal to 1 over the distance between the slit. Okay? The number of line per unit length. And guys, also we can rearrange the equation from based from this equation. Look, number of line is equal to what? 1 over d. D is equal to what? Based on this equation, d sine theta is equal to m lambda. D is equal to what? M lambda over sine theta. Replace into this equation. Replace into this equation. Number of line is equal to what? Number of line is equal to what? One over. And instead of d, write down what? M lambda over sine theta. According math basic reciprocal these two fractions, number of lines is equal to what? Sine theta over m lambda. So this relation is very important, guys. What is the relation between number of line and the angle of diffraction? Is directly proportional. More line, more angle of diffraction. Less line, less angle of diffraction. Okay? Because when the number of line gets more, what happened to the d? D decreases. When d decreases, what happened to the theta? Theta increases. What happened to the width of the pattern? The width of the pattern increases and it becomes wider. So if you have two diffraction grating, as you can see in these two figures, if you have two diffraction grating, number 1 and number 2, which one has more angle of diffraction? Absolutely the number 1. So this one has more angle of diffraction. Why? Because it has less distance between the slits. Theta with d is inversely proportional. But this one, the angle of diffraction decreases and the width of the pattern decreases because d is more, number of line is less. Light is dispersed by diffraction grating, as we studied. The number of lines sometimes is called number of slits. The grating rule with 5,000 lines in 1 centimeter, number of line per centimeter. If the number of line per centimeter is given, how can you convert to d? Number of line is equal to, for example, 5,000 lines per what? Per centimeter. How can you convert this number of line to d? It's very easy. D is equal to what? 1 over number of lines. 1 over 5,000. D is equal to what? 1 divided by 5, 0.2 times 10 to the power negative 3 centimeter. D is equal to 2 times 10. By calculator, you can get this number. 2 times 10 to the power negative 4 centimeter. Why centimeter? Because number of line was given in centimeter. When does the unit of distance between the lines or the distance between the gratings is equal to, it becomes centimeter, if number of line is given per line per centimeter. Is given in what? In line per centimeter. How can you convert this centimeter to meter? Multiply 10 power negative 2, small to large, negative power. So D is equal to 2 times 10 to the power negative 6 meters. So in this way, you can convert number of line to distance between the slits. The greater the number of lines per length, it means that less distance and more angle of diffraction. The less separation between the slits and the further spread part of the individual wavelength of the light area. If the distance between two slits in a refracting grating is 2 micrometer, what is this? Distance between the slits is equal to 2 micrometer. 2 micrometer. Convert to meter. Multiply 10 power negative 6. 2 times 10 to the power negative 6 meter. How many number of lines do we have per meter? Okay, what is the number of line per meter? Number of line per meter, it's very easy. Number of line per centimeter, number of line per centimeter, 1 over D, 1 over this number, 2 times 10 to the power negative 6. Number of lines is equal to 0.5 times 10 to the power 6. Number of line is equal to 5 times 10 to the power 5 lines per what? Per meter. Or 500,000 lines per what? Per meter. Another question, if the distance between two slits in the refracting grating 2 mile, what is the number of line per centimeter? This one, it should be centimeter, guys. This is wrong. Change into the centimeter per centimeter. This question is very important. Listen carefully, please. The distance between the slits is given 2 micrometer, convert to meter. D is equal to 2 times 10 to the power negative 6 meter. How many number of lines do we have in 1 centimeter or per centimeter? Number of line per centimeter is unknown. Number of line is equal to what? Is equal to 1 over D. But this D, it should be centimeter. Now the distance is given in meter. Convert to what? Centimeter. How? Multiply 10 to the power positive 2. Meter to meter positive 2. D is gonna be what? 2 times 10 to the power negative 4 centimeter. Okay? Now number of line is equal to what? 1 over this number. 2 times 10 to the power negative 4, which is equal to 5,000 lines per what? Per centimeter. What is the difference between this question and the previous question only in meter and centimeter? In the previous question, we found number of line per meter, but in this question, we found number of line per centimeter. Well, to find number of line per centimeter, so you have to keep in your mind the distance should be in centimeter. The distance is given in meter, you have to convert to centimeter. Okay? What does the sharpness of the principal maximum and the broad range of the direct areas depend on the number of lines in the grating? Okay? And what does the position of the center bright fringe depends on distance, wavelength, and order number we studied. When, guys, look at this question. When the number of line in the grating increases, number of line increase, distance decrease, theta increase. Does each of the following changes? The distance between the two slits decreases. Distance decreases, look decreases. The angle of diffraction must be increased. Why? Because number of line with angle of diffraction is directly proportional, increase. The distance between formed fringe, the width of the fringe also increases. The distance between formed fringe, it means that the theta on the width of the pattern, okay? Look at question 12. How does the width of the central region of the single slit diffraction pattern change as the wavelength of the light increases? When the wavelength increases, theta also increases, okay? So the width of the central bright also increases. It increases as the light with the longer wavelength is diffracted more, because lambda with angle of diffraction is directly proportional. Question 13. Why is white light separated into the spectrum of the colors when it passes through the diffraction grating, such as in this figure? You can see in this figure, when the white light passes through the diffraction grating, what happened to the light? It's gonna be separated, and the spectrum and the rainbow will be occurs on the screen. The red one has the largest angle of diffraction. So the light of the particular wavelength interferes constructively at a particular angle. Look at question 14, very good question. And so you have to know this question. How can you answer this question? Okay, because I explained it in detail. Monochromatic light shines through two different diffraction gratings. How many diffraction gratings do we have? 2. We have 2 diffraction gratings. The first one, the second one. Okay? The second grating produces a pattern in which the first order and the second order maximum are more widely. What do you mean by more widely? More angle of diffraction. The second grating, the second one, in the second one, theta is more. Why? Because the width of the pattern is more wide. Okay? When does the theta increases and the pattern becomes wider? If the number of if the distance decreases. If the distance is less, small. When the distance is less, number of line must be increased. So which grating, use this information to tell if there are more or a few lines per centimeter in the second grating. More or few? Absolutely, it should be more lines. Why? Because in the second grating, the pattern is more wide. Okay? The pattern is more wide, it means the theta is more. D should be less and number of line must be more. But the second, theta here decreases, D increase and number of line also decreases. The sine theta is inversely proportional to D, which is the reciprocal of the number of line per centimeter. So the answer, the grating that spreads the pattern the most most lines or more lines per centimeter. Okay. What will be the effect and interference occur or diffraction if a red light is replaced by a blue light? The wavelength of the blue light is less than the red light, so the fringe width decreases with the blue light. The red light has more width and has more angle of diffraction. For each of the following colors, the fringe of the interference light is much wider, absolutely red. More narrowed, absolutely slimmer. The violet is slimmer, okay, because it has red has more wavelength, has more angle of diffraction. Violet has less wavelength and less angle of diffraction. Okay. The conceptual challenge, these two questions are skipped. Okay. Okay, spectrometer, a device which separates the light from a source into its monochromatic components. When the white light passes through the diffraction grade, this white light can be dispersed into monochromatic light, into the color of the rainbow. So this is the figure of the spectrometer. Is a device, okay? We have a source of light and a single slit. When the light passes through the single slit, it's gonna be diffract, and because of this lens, the converging lens, this lens can be used to make the light into the parallel lines. So because of this lens, the light becomes parallel and directly hit the diffraction grating. Okay, when the white light passes through the diffraction grating, the source of the white light becomes dispersed because of the diffraction grating, and the spectrum can be occurred on the screen of the spectrometer. And diffraction gratings are frequently used in a device called spectrometers. What we have in the spectrometer? Diffraction grating, lens, and telescope. The main parts of the spectrometer: telescope, gratings, lens. Okay? How does the spectrometer work? The light to be analyzed passes through the slit. Okay? It's formed into a parallel beam. It becomes parallel beam by what? By lens. What is the function of the lens? They make the line into a parallel beam. Okay, the light then passes through the grating. After that, the light passes through all the gratings. So the diffracted light leaves the grating at angles that satisfy the diffraction grating equation. So a telescope with a calibrated scale is used to observe what? The first order maximum, and measure the angles at which they appear. From these measurements, the wavelength of the light can be determined, and the chemical composition of the light source can be identified by using the spectrometer. So the spectrometer is very important to determine the wavelength and to find the chemical composition of the source of the light. What are the uses of the spectrometer? And the advantage and the uses of the spectrometers are very important. Be careful. The first one, the spectrometer uses grating. Spectrometer uses what? Gratings. To what? To disperse the light from a source. Okay? The second application of the spectrometer, to determine what? The wavelength of the light. Okay, so one way to determine the wavelength is the spectrometer. The third one, the chemical composition of the light source can be identified by using spectrometer. One of the advantages of the spectrometer is what? Chemical composition of the light source can be identified. In telescope, guys, be careful. Number 4 is very important. In telescope, spectrometers are used extensively in astronomy. In what? Astronomy. To study what? The chemical composition and the temperature of the stars, interstellar gas clouds, and the galaxies. Okay? So these 4 applications are very important for the spectrometer. Consists of what? Gratings, lens, telescope. The main component of the telescope is what? Grating, lens, and telescope. What is the importance of the using lens? The light to be analyzed, it passes through the slit and is formed into a parallel beam of the lens. An example of the spectrometer presented by the spectrometer is shown in this figure below. The spectrometer are used in astronomy. In what? In astronomy. To study what? The chemical composition and temperature, stars, interstellar gas clouds, and the galaxies. This is one example of the mercury vapor, spectrum of the mercury vapor. The spectral line of each gas is different. Like, for example, the spectral line of hydrogen is completely different with the spectral line of the mercury or of the oxygen or any others. Okay, so the types of the gas could determine by using the spectrometer, because by using the spectrometer we can find and determine the composition of each gas. Guys, that's all, and already we solved all the questions in the section 2 about the diffraction. Thank you for listening. Keep up your best doing.